Hola, me llamo Guy. Hablaré de álgebra lineal in English. Maybe next year in español. Okay. I'm terribly sorry. One moment, talk amongst yourselves. Full screen, Command Shift F. Okay, show me a picture of Hawaii. I went to Hawaii for the committee meeting. We've already seen a picture of what work was like. So that's on top of Mauna Kea. There are lots of mountains. No, there's one big mountain, Mauna Kea. There are lots of telescopes on Mauna Kea. And because we are all big engineering geeks, we decided the obvious thing to do was to go up to the top and take a look at all the telescopes. That's what we did. So what to expect? I'm going to talk to you about representing linear equations, set out the state of the linear algebra proposal. Then we'll look at typical libraries to solve linear equations. We'll look at dynamic and sparse matrices. We'll look at enabling promotion. And then the importance of customizing. If anyone's heard of the Coppersmith-Winograd algorithm, which is very painful, you'll be at home here. Then we'll look at the API. And then finally, we'll look at the impact of all of this on AAA game development. And I'll talk briefly about some recent Twitter storms, if you're interested. So the goals are to provide a linear algebra vocabulary types that mimics those found in textbooks. It's applicable to a wide variety of problem domains, particularly graphics and games, which is what I'm interested in, but also signal processing, large simulations, and so on. It's going to use templates to parameterize the orthogonal aspects of representation. It's got default templates, parameters, and aliases, and this will serve the needs of 90% of all of the users. Okay? But it's got maximal performance on common platforms. The compiler implementers know what the hardware's like, so they can optimize themselves. But it's also customizable for power users to gain maximum performance on specialty platforms. So this is people like people in the HPC community who are interested in high-performance computing. It's got to include element access, matrix arithmetic, and the fundamental operations. And it's got to support mixed precision and mixed representation expressions, such that precision is never lost. So linear algebra is the branch of mathematics concerning linear equations and linear functions and their representation through matrices and vector spaces. But for our purposes, we're going to concentrate on linear equations. We'll always be working in finite dimensional space. So a linear equation looks like this. Are we all familiar with linear equations and linear algebra? Is there anybody for whom mathematics is a completely strange and alien field? I have to ask. I know it's a university, but even so. Linear algebra is central to most of mathematics, after all. But I'm going to look at geometry in particular. So a vector is a tuple of scalars. I pronounce it tuple because I'm a native English speaker. If you hear people say tuple, they're wrong. If it would have two P's, then it would rhyme with supple. It's not, it's tuple. Tuple, all right? Tuple. Everyone say tuple. Thank you. The revolution starts here. I treasure my language. So you can perform addition and the inverse operation, subtraction, if they have the same size, like that. You can perform vector multiplication And scalar multiplication, you've got a row vector times a column vector there. That's obviously the inner product, or dot product. A matrix is a tuple of vectors. And again, you can perform addition and subtraction if they have the same dimension. You also have scalar multiplication. Regular multiplication is a little more complicated. What you're effectively doing is creating the dot product all the way through. The source column count needs to be the same as the target row count. Significantly, multiplication is not, in general, commutative. And there's a special kind of matrix called a square matrix, and a special kind of square matrix called an identity matrix. A square matrix can have a determinant. Geometrically, it can be viewed as the scaling factor of the linear transformation. Determinants crop up a lot, particularly in my line of work. A matrix can have an inverse. A matrix is said to have an inverse if the matrix multiplied by its inverse, or vice versa, is the identity matrix. Not all matrices have inverses. This is problematic. And this is all rather reminiscent of the built-in types. We've got operator plus, operator minus, all manner of overloads, although increment and decrement don't mean anything, and there's no real way of ordering matrices. There's no less than or greater than. All right, is that all clear? We're all on the same page now? So let's look at geometry. So let's consider the general form of a linear equation. Back again. So we can migrate this to 2D with a little substitution, or we can turn this into that. This is just, again, simple substitution. We're swapping A1 and A2 for A and B, swapping B for C. That becomes by equals negative AX plus C. And since B and negative A are arbitrary constants, we can see that y equals mx plus c, which is the very familiar equation for a straight line. We've all seen straight lines, haven't we? Yes, Guy. Right, okay, thank you. So we can see that any straight line can be represented with a linear equation. Okay, so generalizing to 3 dimensions, you can see how this might work for planes and so on. So representing a coordinate pair as a vector, we can translate, scale, shear, reflect, and rotate this vector. So translation takes place by adding the translation to the coordinate pair. Scaling works by a scalar multiplier, or we can achieve the same effect with a matrix multiplication, although why you'd want to do that eludes me. Shearing means scaling x and y, but by different amounts. So we achieve that like this. Reflecting means multiplying a particular ordinate by -1. And rotating is slightly more complex. If you still remember all your high school geometry, though, this will present no problem at all, I'm sure. We can actually stack multiple operations by multiplying matrices. So if we want to reflect and then shear, we can do so like this. And this means that if we want to carry out the same operation on a set of pixels, on a set of points, in a mesh, for example, then rather than carrying out, say you have 200 vertices, rather than carrying out 400 operations on all those vertices, 1 to reflect and 1 to shear, we can carry out 1 operation to calculate the combined matrix, and then we're down to 200 operations again. This is fantastic. I can't overstate how amazing matrix multiplication is. So I can do better than this. So who here has actually written a linear algebra library? Besides the committee members. All right, now including the committee members, who's written a linear algebra library? Excellent. Who's written 2 linear algebra libraries? 3? 4? I've written 4 linear algebra libraries. I dug out my notes from nearly 30 years ago. 30 years ago. I've been writing games for about 30 years. So this was quite a way into my career. So 30 years, I wrote my first linear algebra library. I used fixed point arithmetic. I was on a 286 PC, and I had no maths coprocessor. Imagine life without a maths coprocessor. We all take floating point arithmetic for granted. Oh, it's easy. I'll just type float, 3.7 times 8.9, blah, there we are. And it takes, 6 cycles? It's easy. Well, it's only recently easy. Anyway, I wanted to use SI units, because I'm European. I like Standard System International for the win. But with 16-bit fixed-point arithmetic, I decided I would reserve 4 bits for the fractional part. So this gave me 6.25 centimeter resolution. And that's fine. 6¼ centimeters, that? I could represent huge distances. So my next one exploited the floating point coprocessor that shipped as standard with the 486 processor. Then I made use of the SSE2 instruction set. Right now, I have a revised version of that running at the moment with AVX instructions. I think it's the Sandy Bridge processor. One of these days, and this is the 5th time I've given this lecture, I'll actually check that that's true. But I'm a game developer, so my use of linear algebra was strictly limited to matrices with between 2 and 4 rows and columns, with a non-integer scalar type. Now, I've got several optimizations available to me. I know how big all my matrices are going to be. The scalar type is always a 32-bit floating type. I know about my target processor, so I can use the intrinsics and the SIMD instructions. I can make use of the cache. But my library is optimized for this particular usage. I write games for PCs. There we are. I don't write games for embedded hardware in Tesla motor cars. I write games for PCs. Everything is fixed size, everything is dense. And there are many ways to optimize for other situations, such as sparse matrices, where you just have entries here and there and a lot of zeros, or variable size matrices that grow as you perform calculations on them, if you're, for example, reading data from during execution. But it's like string classes. Who here has written a string class? I'm delighted. Now, 10 years ago, I asked who here has written a string class. I've got a forest of arms. But there was a time, during the 90s especially, everyone was writing string classes. I can write a better string class than this. I'm going to lose this shortly. Hang on. Anyway, there are quite a few libraries out there already. So I took a look at Wikipedia and still found plenty more than I actually knew about. So let's take a look at some of them. So who's heard of BLAS? Good. Yep, that's the one we all know about, really. First released in 1979 as a Fortran library. It prescribes a set of low-level routines for performing common operations. There are C bindings, that's handy, and there are many implementations optimized for speed on different machines. There's the C++ API, which of course is called BLAS++ because we have no imagination. And that implements much of the functionality for your linear algebra needs. There's an example function. You can see it's taking explicit types there. There's also, of course, boost.ublas, but that hasn't been contributed to since 2009, which means no constexp, no except. Not good for me. There are 3 levels to the BLAS API. This is level 1. It contains all the vector operations. Level 2 contains the matrix vector operations. And level 3 contains the matrix operations. The reason why I'm showing you this is it's a good starting point for an API. You can see a fair amount of repetition, okay, which is varying on matrix type. So we've got Hermitian, symmetric, and triangular matrices. And operands, whether it's matrix vector or matrix. And the set of operations is different for vectors from matrices. Who's used eigen? Yeah, eigen's nice. Significant advance over last. It's huge. If anyone's actually taken a look at the document, it's massive, but it is thorough and it's comprehensive. It's got a selection of class templates for matrices, vectors, and operations. And it accommodates runtime as well as compile time sizes. And it has a mechanism for dealing with non-owned data. If you've just got a pile of data coming in and you just want to kind of superimpose a matrix view onto that, you can do that. Okay, how many member functions does string have that aren't special functions? Who thinks more than 10? More than 10. Okay, who's used the string class? Okay. All right, I'm going to stop this part. There are 45 member functions in string, and this is excluding the various constructors, and there's 45 special functions. That's a lot. It's something that I dislike about eigen. The API is entirely constructed from member functions. I think we've had bad experience of rich member function API that Arno was alluding to earlier on in the first presentation. I don't want to repeat that with linear algebra, particularly since there are so many things that may be required, decompositions and things like that. BLAS++ offers 32 member functions. Now, the Eigen tutorial offers this sample program. It's quite easy to understand, I think, and I like the initialization at the bottom of 1, 2, and 3 being commaed via a chevron operator into V. It's very readable. Anyone use dlib? Worth a look. Take a look at dlib. It's at dlib.net. It's a big library of useful things, including matrices. It takes an interesting approach to matrices by deploying expression templates. Who's heard of expression templates? Yeah, very much hard to grasp, but incredibly useful. So this idiom was described by David van der Voorde and Todd Veldhuizen around about the same time, actually. So it's a template metaprogramming technique. So you're all scared already, I can tell. And it builds structures representing a computation at compile time. So expressions are evaluated only as needed to actually produce efficient code. It allows you to bypass the normal order of evaluation, and you can achieve great optimizations like loop fusion. I've offered a brief overview. If you look for other versions of this talk, you'll see a deeper explanation, but time's short. Now, let's look at everything you need to know about storage. Storing your matrices, it's quite the topic. If you're using a fixed size matrix, then you can most likely just keep it on the stack. But if you're using a sparse matrix, or you don't know the size of the matrix until runtime, you'll need to be able to allocate memory on the heap, or wherever you're keeping your free store. Or you may not own the values that make up the matrix. What if you've got a stream of scalars coming in, and you know what the stride is, and you simply want to span? And let's not forget cache requirements. How big are your cache lines? How do you want to store an array of matrices? Do you have access to SIMD instructions? And which set do you have? And how big are the integers, the registers? And how many do you have? How many registers do you have? And does your tool set expose intrinsics? These are all questions that we have to accommodate. Much of these are implementation details. And the purpose of standardization, and this is the important takeaway, is to define an API, not to define an implementation. The API should accommodate any implementation you can throw at it. Now, the obvious solution is to parameterize your storage and standardize how you access the elements. So let's introduce our first class. Fixed size matrix. So this is just a storage class. So what sort of things might I want to do? I might want to know the number of columns and the number of rows, but I've already got that in the template parameters. Maybe I want direct access to the data. So we have the function operator there. One thing I'd really like to do is a square operator accessor. We can't do that at the moment, but there's proposals working their way through which will allow me to say open square, I, j, close square. Really looking forward to that kind of thing. The scalar type name is an ideal candidate for a concept. If you've been following the concepts development, you might think scalars are exactly what we need there. But what if you don't own the data? But what if I told you that there is already a proposal to add a multidimensional data view to the standard, which is in fact the case. This is P0009, paper number 9. So it's been around for a while, several years. It's working its way through the library working group. I'm not sure that it will make C++ 20, which is a bit disappointing. No, Timo's shaking his head. No, it's a lot of words. It's just a big, large number of words. So I don't think it'll make it. But so this means that we need our next class, which is matrix view. So we have to expose the scalar type. So we do that through a using declaration. There's no initializer list construction because we don't own the data. We have to retrieve the rows and columns by querying the mdspan objects. That's what P009 is all about, mdspan. And this looks not too different from the fixed size matrix. These matrix classes rely on you knowing at compile time how big things are going to be, which is ideal for my traditional domain, but for data harvesting, rather less so. Perhaps data is arriving and you want to periodically grow a matrix with additional rows, which means we have to drop the row and column parameters and we have to replace them with an allocator. So how about this? dynamic size matrix. So nothing too surprising there, I hope. We've got columns and rows, but we have pretty much the same shape. But we're looking at a container now, so we need the column and row capacity, and we need to be able to reserve and resize. Things start getting a bit unpleasant, really. Anyway, I'm hoping that these three will feature in the proposal, but of course there's nothing to stop you from specifying your own and simply slotting them in. Your own storage class might have more exotic purposes. Right, quiz time. Anyone here use C++ for performing arithmetic? Come on, all of you, surely, use C++. All right, who here uses C++? Does anyone use? Right, okay. Right, arithmetic. So these are standard interview questions, so take notes. What I want to know is the type and value of A, please. Yes. It's an int. Do you know what its value is? Sorry? 11. Yes. Congratulations. What about this one? Ooh, 11, yes, but now it's a long. Right, what do we think of that? Oh, This trips up everyone. It's an unsigned long with value 0. Okay? Because -3 unsigned long will take the bit pattern, which is a load of ones, and then interpret it. And once you divide this small number, 35, by this huge number, that will give you 0. On we go. Same problem. So let's change tack a little. What about this one? Whoa. Double. Well done. The decimal point annoys me, but Koenig and Ritchie said it's okay, so I can't really disagree with them. What about this one? Yep, that's easy. What about that? Okay, I think you're getting the hang of this now, aren't you? But I love this one. Yeah, you all thought it was going to be unpleasant, weren't you? What about that? Ooh. I could do this all day long. There are many traps to set for the unwary traveller. But what I'm really talking about here is implicit conversion. That's the important thing. So who knows their promotion and conversion rules? Really? Really? Do you really? Never say that you know your promotion and conversion rules to me during an interview. Because then I will ask you. Right, I'll tell you what. Small integral types, they can be promoted to large integral types. Arithmetic operators do not accept values smaller than int. So that's fortunate, we're only dealing with int and larger. Float can be promoted to double without change in value. Conversions may change the values with potential loss of precision. With integral conversions, sign and width are important, obviously. Floating point conversions are a little more forgiving, although converting doubles outside of the range of floats is, of course, undefined behavior. Floating point to integral conversions merely discard the fractional part if it can't fit its undefined behavior, and integral to floating point conversions return the nearest value. Look at cppreference.com. I hope cppreference.com is on all your bookmarks. It's a marvelous repository of information. So arithmetic is very, very well defined. The C++ built-in arithmetic types freely promote from float to double, or from int to long, and freely convert from integral to floating point. That is amazingly useful. I'm going to reinforce that. I hear it incorrectly stated often. Promotion, float to double, widening representation. Conversion, integral to floating point, changing representation. So imagine not having that flexibility available to you. It would make life pretty hard, wouldn't it? Because we'd have to explicitly promote everything up to the widest type and then narrow it, or up to long double, and then narrow everything back down again to the type you're interested in. And that's a lot of bookkeeping, a lot of ugly casting. Although, who's heard of ftol? Yeah, right, so ftol caused me terrible trouble in game code. It's the implicitly called function when you write something like this. Ooh, nasty. It's an expensive function, and it has to be called at runtime. Chews up cycles. It's hundreds of cycles. Quite often, I found in the code that I was reviewing, that int on the left was just arbitrarily chosen, and then suddenly it would be passed to another function which took a float. So the int would be then converted back to float, and then I'd find the person and beat them around the face and neck with the sense of it. You know, when auto appeared, I was absolutely delighted because with auto there, you get the right stuff, and only conversions only happen when you actually need them. So if you have a matrix of int, and you add a matrix of double, then you should get a matrix of double. Right, who's heard of this struct, common type? Okay, see a number of you. So it provides the type that all the parameter types are convertible to. So we'll need to provide specializations for our matrix types. But things get a little complicated for complex numbers. Has anyone used std complex? Okay, it's worth it. It does work, it does all the business. So quiz time again. But I'm not going to, do you know what? That's the answer. That's the answer. Why is it 17? Ah, there we are, that's more like it. So a float times int divided by a float. Malformed. That's awkward. So does this obey the principle of least astonishment? Should the compiler be able to evaluate this? I actually think that this is a defect in std complex. And what should happen is that the promotion of the scalar type should be reflected in the return type template parameter. And if anyone wants to write a proposal to correct this, I'll be delighted. I'm a bit busy right now. I have linear algebra to do. And while you're at it, can you make it no except constructible for all no except constructible scalar types? I'd be super delighted if you manage that. But linear algebra, we need to specialize our element promotion for std complex because that type admits no conversion or promotion. That's what the problem is. So you might be asking yourself, do you know, is it really worth all this furniture? Do we need this? When am I going to need a matrix of complex numbers? Quaternions? And there's another problem. What if you want to operate on two matrices with different storage types? If you have a fixed size matrix and a dynamic size matrix, that still needs to work. There needs to be conversion. So we need to describe a system of conversion for storage types as well as scalar types. I won't go into that here again. So we've covered storage and promotion. Now let's look at operations. We want to add, subtract, multiply, and divide by scalars and multiply by other matrices. How we do that depends very much on what you're doing. For example, the naive way of multiplying a matrix is to iterate through the rows of the source matrix and multiply by the columns of the operand matrix. However, you may know that your matrices contain lots of empty rows or columns, if you have a sparse matrix, for example. And you might want to flag that up so you can speed things, you can improve things. But that's a different algorithm. So how do we enable the user to choose their own algorithms? It's another customization point. So let's look at what we have to customize. So, vectors. They have special operations that come in useful. These are the inner product, modulus, and unit vector. So we can look at a naive implementation for each of these, and inner product is already defined in std. Who knew that? Because I didn't. Okay, good for you. Read the standard, all 2,000 pages of it. Good bedtime reading. So it would be a case of simply forwarding to that function. We'd have to put it in its own namespace, I imagine, but you know, more of that later. Modulus is again quite trivial. We provide two functions, modulus squared and modulus, that look like this. Modulus is obvious. And finally, unit vector. It's actually quite trivial. We're just going through and finding the modulus and then dividing each element by the modulus through a lambda via std transform. So all matrices and vectors can be transposed. Transposed would look like this. These are all const extra functions, by the way, which is handy. And it should be possible to simply provide a transpose view on a matrix so that you don't need to copy it. If you just want to take a matrix and then multiply the transpose by something else, then being able to read the columns and rows the other way around, that should work. There's nothing to prevent that. So next we have a submatrix, which pulls a matrix out of another matrix by masking a column and row. Again, naive implementation. All these slides are going to be available afterwards, by the way. You don't need to take photos. Just believe me, I'm short on time. Right, the identity matrix is the matrix which leaves matrices unchanged under multiplication. So that's just a load of ones down the leading diagonal. And so that's our set of functions. It's a bit of a beast, but we have a struct called matrix operations, and then we have members which perform the operations. They need to perform conversions, so they're function templates returning auto. So we can put them in a struct and template them over a storage type. Dynamic matrix, fixed size matrix, view matrix. And what's significant about this set of functions is that some of them are deeply non-trivial, particularly inverse. There's a large body of work which describes different approaches to take depending on the nature of the matrices. Let's take a look at multiplication. So worst case multiplication, to multiply two n square matrices requires n cubed multiplications of scalars and n squared minus n additions, which means the complexity is O n cubed. Although there are cache considerations to bear in mind, those cache considerations really make a nonsense of big O notation. Controversial. The ubiquity of matrix multiplication, it is everywhere. It's inspired a lot of research into superior algorithms. Anyone familiar with Stratton's algorithm? Okay. So that's got a complexity of O(n) to the power 2.807. I think that's just nutty as all. But anyway, but there's been a race to minimize over the past 50 years that value. As of 2014, that complexity number has reached this. Well, anyway, there's been research into Gaussian elimination, matrix inversion, determinant calculation, all for the same reason. It's incredibly popular and incredibly hard to do well. And so we have hundreds of handy algorithms for particular types of matrix. But we cannot require clients of this class to use a particular algorithm. So this means we have a second customization point, the set of algorithms. So you can have my matrix ops rather than matrix ops. So you'd simply choose your own operations and maybe forward to the ones that the standard supplies. So let's put all this together. So we have a storage class and an operations class. But neither of these are what we want for our users. We want a matrix class and we want a vector class. That's it. And maybe we want to put them in a namespace called LA, because there's an awful lot of overloaded symbols going on here. So let's look at these classes. First of all, note the scalar T and the matrix T types. They're inferred from the rep type. And you can see a selection of constructors. This isn't exhaustive. This is just a partial exposition. I imagine we'll get ranges in there as well, because it's 2019. So we've got constant, non-constant access as well. It's, again, nothing too surprising, I hope. We have equality operators, scalar multiplication and division, addition and subtraction, and finally the data itself, matrix T, which, if you recall, was inferred from the template type. And then we have non-member functions, scalar binary operators for multiplication and division, and then we have some matrix functions, transpose, submatrix, is identity. And then there are the matrix binary operators. And at the end, you can see the identity function. Then we have the vector functions, inner product, modulus, modulus squared, and unit. There's scope for adding still more non-member functions. And this is why we're saying the matrix class is actually quite small. We do everything in free functions rather than loading up the interface. It becomes easy to add extra functionality. There's a single template operator, REP. So what do we deliver to the standard? Well, out of the box, we need to deliver something immediately useful and sufficiently performant. So I think we should deliver the matrix, vector, an operations class, and the fixed size and dynamic size storage classes. And if MDSpan makes it through to LWG before this proposal does, I hope it does, then the matrix view storage class should also be added. Now, how do we teach all this? What are we going to tell our students about using these classes? All of you, at some point, are going to have your own students, your own disciples, who will learn C++ at your knee. Now, assuming your students have a knowledge of linear algebra, and assuming we get the classes to behave without astonishment, with conversion and promotion, similar to the built-in type, so that's quite a long list, there shouldn't be anything to teach. It should just work, as assumed by the user. You write it down and it does what you expect. This is the joy of the principle of least astonishment. So a row vector, a vector multiplied by a vector should create a scalar. It'll be a dot product. A mismatched vector addition should fail to compile, or it should report an error under contracts. Are you all up to date with contracts? I know Daniel's up to date. You know all about contracts, don't you? Yeah. A little bit, good, yeah. Talk to him about contracts. If there's one thing you want to do today, talk to him about contracts. They're amazing, and they change the language in a really administrative way that makes things really... I love contracts. Thank you for your work. Thank you for your service. But they should reduce the quantity of exception handling throughout the language. And ideally, they eliminate the vast majority of exception throwing from the standard library, which for me, where I work in a no-exception environment, is really, it's exactly what I want. So let's rewind the goals. Provide linear algebra vocabulary types. Parameterize orthogonal aspects of implementation. Use templates. Defaults for the 90%. Customizable for power users, element access, matrix arithmetic, fundamental operations, and mixed precision and mixed representation expressions. Job done. But, and it's a big but, AAA game development. So, we're a tough crowd, to be perfectly honest, in AAA game development. We live and die by frame rate, by how much we can achieve in 1/60th of a second. Okay? Every cycle counts. If standard library code generates inferior code to our own hand-rolled efforts, it's discarded. We don't use it. And then we have to worry about compilation time. So when I started out in game development, if the build and run cycle took longer than 1 second, I was frustrated. And this is really significant and something that regular developers probably overlook. We don't design a game and then design the tests and then write the game and then walk away. That's not how game dev works. More than in any other domain, design is iterative based on immediate feedback from play. So when I started writing games, I would expect to change a line of code and see the effect within seconds. That just doesn't happen in C++. I used to write an assembly. Bang, 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 change, bang, change, change, change. Ooh, nope, crash there. Ooh. I could iterate my way through a game in next to no time in a way that I simply can't nowadays in C++. Now, this library that I'm proposing is quite template heavy and will impose a burden on build time. And then we have the matter of missing functions. Matrix inversion and determinate, vector cross product are functions that I will call millions of times per frame. Now, of course, game devs can take the matrix library and specialize the classes for geometry and add the appropriate functions, but perhaps they will need extra convincing that that's all they should do rather than rolling their own specializations. But even if they do, at least I will have provided an API to describe how it should be done and the identifiers to use. That's the important thing. Or maybe, I'd like to actually tell you about my next paper. A specialization of linear algebra for Euclidean geometry. So I should be working on this in the coming months. I hope to have something to present in Belfast at the end of the year. Yeah, you weren't expecting that, were you? Whilst I'm here, sorry, it's contractual obligation, we're hiring. We have a one-year intern program, if anyone's interested in one-year internships. Funny you should mention that. Has anyone heard of includecpp.org? So this is a diversity initiative to improve diversity and inclusion in the C++ community. It's overwhelmingly male and white, which is all a bit wrong. And if you search for my name in YouTube, you'll see me giving lots of diversity and inclusion talks. So you can go there for jobs. I'll be very interested to hear from you. Thank you for obliging me, Daniel. So there we have it.
For your talk. So, I I see hands over there.
Ah.
Hi.
Hello.
Thank you very much for your talk. It was
very
very
welcome.
interesting. I was really looking forward to it because,
Oh.
big disclaimer, I'm not a software developer engineer. I'm just a regular engineer. And I passed on to development because we have actually the need to implement algorithms mostly based on linear algebra in embedded systems, which only accept C or C++.
Yep.
And I know all the drill about, BLAS, Open BLAS, and my question is about an even higher level API. If there are any considerations, like have you ever looked at Armadillo C++, for example, that provides an API that, maybe not here, but in most of the engineering areas, MATLAB is widely used, and the API is very, very similar, really easy to use. Like, it would really widen the audience for a linear algebra library if it was like more, less technical in the C++ side and more like friendly in the engineering side.
Yep. We looked at a lot, and I'm not kidding when I say a big lot of libraries before we got started. The real problem that we have is that there are many, many domains of linear algebra usage. My domain is game dev. My co-author, Bob Steagall, his domain is imaging, medical imaging. The machine learning crowd, they jumped on this like there was a big dog pile. And so what we decided was the thing to do is actually to deliver this in layers. So this is layer 0. It's not even layer 1, it's layer 0. Actually, it is layer 0. I'm a C++ programmer. Everything starts at 0. This is layer 0. All we do... No, really, layer 0. It is that foundational. It is that fundamental. It is layer 0. It is just the type, just the matrix type, just the vector type. I'm expecting succession papers, and I've already been alerted to succession papers from different domains that will take these and specialize them to make more friendly interfaces. This is why I don't have member functions in these classes. The idea is that you can specialize it more appropriately for your domain and then move it on there. If you want, Klaus Eagleberger is the author of Blaze, and he's looking at re-implementing Blaze entirely in terms of this library. It's going quite well, apparently. And that's what I expect. So although we would expose matrix and vector in the standard, I would expect that in the power users would specialize still further for their particular domains. Does that answer your question? Yeah. Good, thank you.
Any other question?
Okay, thank you for your presentation. I'm guessing in the game development world, you try to move all these linear algebra computations to the GPU in order to parallelize it.
Yep.
Which library do you use, or do you prefer to use, in order to do that?
I can't tell you. If I did, I'd have to kill you.
Fair enough.
Seriously, I can't tell you. I'm sorry.
Okay.
Next question.
That's it. Thank you.
No, really.
I
can't say. I absolutely can't say.
Let's not kill anyone.
No, let's not kill anyone. I'm joking. Obviously, I've never killed anyone. I don't plan on doing so.
Okay. Any other question that does not require murdering?
Oh, wow. I'm here all day. If you want to talk to me.
Yeah. So for the standard library, then, are you going to base the implementation of? You mentioned already BLAST, but there are these other implementation that specialize when you compile them to the architecture.
It's not my decision.
All right.
I simply provide an API. The implementers provide the implementation. They can do what they like. That's the genius of the standardization process. Is it simply says it should look like this, but you decide how it's implemented and how it operates. Okay. So for example, Microsoft in Visual Studio, they may use DirectX Math to achieve all their matrix operations. But Jonathan Wakely in libstud C++, he doesn't have that available to him, so he might have to you know, I think the best way to do it would be to use the const extra functions of stood algorithm, of the algorithms, because they can all be implemented quite naively, and then allow people to, you know, slot in their own if they so choose.
Okay. So we are required to implement all the underlying algorithms?
No, you're not required to implement any at all. By specifying this API, implementers are obliged to implement it. So out of the box, you'll have it straight away. If the performance is insufficient for you, you can specialize those bits which are too slow.
All right.
That's why we have so many specialization points. If you decide, do you know what, this multiplication is ridiculously slow, I'm going to stick in my own algorithm, then you can do that. You can but that's the only bits that you need to specialize. All the rest of it you can leave untouched. You don't have to completely re-engineer the entire matrix library.
All right, I got it now. Thanks.
Yeah, and as for any other component of the standard library, let's leave implementers room to compete in quality of implementations.
Yep.
And at the end, you will get the library with the best implementation, or you just switch to a different vendor. That's it. Okay, guys, thank you very, very much for your interesting talk. I'm willing to use this, so thank you.